I'm Anil Kumar. Welcome to my series on mechanics. In this video, we will learn applications based on Newton's second law of motion. I'll take up three examples, and all the three are in the state of non-equilibrium. We'll understand what is this state of non-equilibrium and how is it explained by Newton's second law. In case you want to learn from me, you can always send an email on the address given and contact me on the globalmathinstitute.com website. So in this video, we're going to discuss Newton's second law of motion. With this law, we can actually state when is the system in equilibrium and when it is not in equilibrium. We know that the Newton's law actually relates mass and acceleration, and that's kind of important to find the relation F equals to ma. When we do this, we also need to have some assumptions which we'll talk in details. We'll make free body diagrams to solve most of our questions, and all these examples will help us to understand the applications. We'll find generally acceleration of the masses and find the tension in the cord. Three examples which I am going to take are listed here. In the first example, I am going to take masses on a horizontal plane. You could connect any number of masses in the horizontal plane. If you move them, all of them will move with the same acceleration, right? And the tension in the string will also be constant. We'll see how do we calculate these two things. In the second case, what I've done is, second mass I've actually dropped from here, and then we have one mass left on the table, the other one, with the help of a pulley, is connected with a cord and is kind of. Force of gravity acts on this, and that is the external force. Now, this external force makes the system non-equilibrium. So when this external force is there, the whole system moves with a constant acceleration, and this acceleration is due to gravity, right? Now, we'll calculate again the tension in this particular string and also the acceleration with which the system is moving, right? And in the third case, what are we going to do? Well, we'll hang them with a pulley, as shown here, right? So basically, you find that these are the three cases which, if you understand, you can actually solve any question from your book related to such problems, correct? And the results are so much related. Once I give you this summary, you'll be amazed how easily we can actually solve such questions, correct? So let's begin with the second law itself. Now, what does the Newton's second law of motion states? Well, it says that the acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to its mass, right? So that is what it is. Directly proportional, and we are relating acceleration with the net force. So acceleration is directly proportional to the net force. Sigma F is the net force at a particular point, right? So objects we normally say will be treated at a point. So if this is the point where we are trying to find the net force, then at this point we actually, let's say this is one of the forces, then we are going to resolve the force in x and y directions, correct? So this can be resolved in x and y direction. So that becomes the fx1 and this is fy1 component of this force. Similarly, if I have some other force, for example, I could have a force like this, right? So if I have a force like this, in that case, this force could also be resolved into x and y direction, correct? So here the force could be represented at Fy2 and this could be Fx1, 2, right? So likewise, we could have many forces. When we say the net force, we are trying to find the sum of the forces in the x direction, and then we'll also find the sum of the forces in the y direction. Do you see that? All these. Now from here, we can always find the net force. So F net, let me say, F net, which we are saying is this sigma, right? Is the net force. The magnitude of this force will be equal to square root of the sum of these forces, right? Sum of these forces along the x direction, square of that, plus sum of these forces along the y direction, square root, correct? So that becomes the magnitude of this particular net force, correct? And direction you can find with tan theta. So the direction of these forces, when you resolve them out, you will get some direction, correct? So which you can find with tan theta. So the direction will be given by, let me write down here, tan theta, the direction will be given by the magnitude ratios of y and x, correct? So, so this is sigma of fy over sigma of fx. That should give you the direction. So that defines the net force at a point. So that is how we are going to calculate the net force. I hope this concept is absolutely clear to you. And what we are saying here is that if this net force is not zero, in that case there will be acceleration, and then they are related with the relation that net force is equals to m into a, mass into acceleration. Is that clear to you? Correct? So in short, if the net force acts on the system, that means that the sum of these forces is greater than zero. The system has an acceleration, and then this net force is equal to the product of mass and acceleration, right? This leads to non-equilibrium situation. So when this net force is not equal to zero, then it is non-equilibrium situation. Correct? So you understand non-equilibrium situation clearly. Net force is not equal to zero means non-equilibrium situation. So what is equilibrium situation? Object is in equilibrium if the net force acting on it is zero. So if this is zero, then we are talking about the equilibrium situation, right? So when I say that net force is equal to zero, that means mass into acceleration is also zero, right? And that really means mass cannot be zero. That means that acceleration is zero. So it basically means that the system at every point, the acceleration is zero, correct? That is what it says. Now, if an object is moving with constant velocity, will the object be at equilibrium? That is a question to be answered, right? Constant velocity means acceleration is zero. Perfect. And therefore, we have the conclusion that object is in equilibrium if it is at rest or is moving with a constant velocity. So there are two conditions for the object to be in equilibrium. So when it is in equilibrium, it is at rest or moving with constant velocity. So it is very important to note both the points. So if I say that the two objects are there and they are connected and they are moving with constant velocity, right? That means the system is in equilibrium, right? Because the acceleration is zero. So mass into acceleration will be zero, net force will be zero. So I hope this point is absolutely clear. Now let's also look into the units of force, right? So many times you have different units of forces which we need to connect. So globally, we have three standard units: SI or MKS units, CGS units, and the British units, correct? So when we talk about the SI or the MKS units, the force is represented in newtons. When we talk about CGS, the force is represented in dyne, and pound represents the force in British units, correct? Well, the formula is same, F equals to ma, and mass and acceleration. Well, acceleration is meters per second square in MKS units, and mass is in kg. So 1 Newton is basically equal to the product of kg and mass per second square, unit weight, right? In the case of CGS units, we are talking about grams and centimeters per second square, and in case of British units, mass is measured in slug. So that may come as a surprise to many students. And feet per second square is the unit for acceleration, correct? So 1 pound is one slug into feet per second square, correct? Now the relation between the units is that one dyne is equal to 10 to the power of minus 5 newtons. Well, clearly that is the case because, 1 meter is equals to 100 centimeter, correct? 1 meter is equals to 100 centimeter, and 1 kg is equals to 1000 grams, correct? So that makes those five zeros which we are talking about, correct? So 2 and 3 five zeros, correct? So you could say that 1 Newton is 10 to the power of 5 dynes. You could say that also. That means 1 Newton is equals to 10 to the power of 5 dynes. Clear, either way. So that is how you could relate. Now, this is a very difficult conversion. The slug is defined as what? One slug one slug will be what? One slug will be a force of 1 pound if the acceleration is 1 feet per second square. Correct. So one slug is the mass which will undergo an acceleration of 1 feet per second square when the force of 1 pound is applied to it. Correct? Right. So when you convert these units, remember that 1 pound is basically 4.45 newtons. So that is a very handy formula which you may use many times. So kind of underline this formula and try to relate this relation if required, especially for my students in UK. Okay. Now, let's understand 1 kg. Well, 1 kg you can see is the mass which will undergo an acceleration of 1 meter per second square when a force of 1 Newton is applied on it, right? Standard. Many times you are supposed to explain the unit itself, and there it comes very handy. Let's also look into the assumptions as we are moving along. All real situations, all physical real situations which we come across, we try to give a mathematical model to those situations and then work out some values. So we do make some assumptions in doing so. So these are very important assumptions. You can actually pause the video, read and understand them all. Let me go through them. When a flexible cord pulls an object, the cord is said to be under tension, right? And the force it exerts on the object is the tension Ft. So, what I'm trying to say here is that if I have this object, let's say if I have this object here and it is being pulled by a cord, let's say like this, correct? So, in that case, is there is a tension in this, right? So I'm calling this tension as the force of tension T, correct? Now this tension acts in the opposite direction. We'll understand this also. So chord is inextensible with negligible mass. So what are the assumptions on the chord itself? Chord itself is inextensible whenever we are saying it is with negligible mass. That is important to understand, right? Flexible chord can only pull and cannot push. So when we use the term flexible, we're trying to pull it, right? We cannot push the object by a flexible chord, right? This is important to understand. It's not a rigid body. Now, clearly, the light object means what? Mass of the object is negligible compared to the other masses. Then we say it is light, right? And then also the force exerted at one end is transmitted undiminished to each adjacent piece of cord along the entire length of the other end. So that is to say that if I connect another mass here, right, then we have the same force exerted on both the sides. That is what we're trying to say here, okay? So basically, what we're saying is that the tension is the same at both the ends of a light string. So that makes some sense to you now, I think. So tension is the same at the end of both the strings. So when we work out examples, we look into this aspect that helps us to make a free body diagram. Okay, once again, inextensible string means it cannot be extended. Well, clear. But then what does it mean physically? String that does not stretch, correct? It's not a spring or something like that. It cannot be stretched. Acceleration is the same in the object at both the ends of a light string. That is what we're trying to say. So if I pull this object, right, then in that case, the acceleration A is same for both of them, right? So both of them are moving with the same acceleration. That is what it means, correct? So it's very important to understand that the acceleration is the same at both the ends of the light string. We'll also take up an example with the smooth and light pulley. And there, what are the assumptions? Well, the assumption is that pulley has no mass and will neglect rotational inertia. And that's important because no force is not required to actually move the pulley, right? That is important. So what we'll do here is that we'll actually pin the pulley in the center. So all the mass in the center, let's say this pinned. And now we're looking into the objects on either side. So clearly, when this moves, no work is, no force is applied or wasted in moving rotationally the pulley. That's what we are saying. So neglect rotational inertia, right? And then the tension is the same on either side of the pulley. So this tension which is there on the string is exactly same on either side of the pulley, right? So this tension is same on either side. That's what we are trying to say when we say it is a smooth and light pulley. So I hope these assumptions are absolutely clear. Now we have the foundation to start with our examples. Let's begin with the very first example. Example 1 now. Example 1. We have connected particles, so we'll consider these masses on the table. So the question here is, two boxes with mass of 12 kg and 10 kg are resting on a table. The horizontal force of 40 Newton is applied by a person to the 10 kg box as shown in the figure. Find acceleration of each box. Find tension in the cord. So this is this additional force of 40 Newton being applied, and this is the cord, which is inextensible, right? Very light. So all those properties and assumptions should now be clear to you as we go along. These are the two masses, 12 kg and 10 kg. We label them as M1 10 kg mass, M2 12 kg mass, correct? Now what is going to be our strategy? Well, our strategy will be first to draw a free body diagram or the force diagram, describe the assumptions, relate parameters, and then solve the equation. That is what we're going to do, right? So also note that particles connected by inextensible string moving in the same direction can be considered as a single system. What I'm trying to say here is that you could also make one system kind of like this. This will be treated as a single system. We'll look into this part later when we derive the formula that yes, if I could have made them as one system, that means a mass of 10 plus 12, which is 22, 0.0 kg. In that case, I could have very easily solved this question. Do you understand what I'm trying to say? I could say this, right? So if I add them all, then in that case, the big mass will be what? Will be 12 plus 10, which is 22 kg, correct? And we have a force F which is 40 newtons, correct? So we know what? We know F equals to ma, or we know actually A is force over mass, right? So force is 40 newtons and it is 22 kg, right? Uh, so force is 40 newtons and the mass here is 22 kg, correct? So that becomes the acceleration. Do you see that? So how easily we could actually find the acceleration by just dividing the force by the total weight in this case, right? So mass, total mass, which is 22 kg, right? So that is how we could actually find. This is very simple. If you see that the two particles could be actually taken as one system. Well, let's go through all the concepts and check our results. Okay, so first thing first, we're trying to make the diagrams, right? We call this as a free body diagram or the force diagrams, right? Any terms can be used. So let's look into the first mass. The first mass here is 10 kg. It's being pulled with a force Fp. So I'm not writing the values here. We make a general solution, right? So we are actually doing a general solution. Okay, so we have a force Fp, and this force will cause a tension in this string. Now, this tension is acting in the reverse direction, and therefore we have Ft in the reverse direction. It is due to the tension in the string. Now, since the string is inextensible, therefore, and is also treated as a light string without any mass. In that case, the same force is applied to the second body. So the second body is actually M2, which is now exerted by this tension. Now, this tension this time is going to pull it because it is going to act in the opposite direction. Do you see that? Perfect. Now let's see vertically. Vertically, it is the weight which is acting downwards. Force of gravity is pulling it. That causes opposite, equal and opposite reaction, and that is called the normal force, Fn. So in the first case, I'm writing this as Fn1, and the second case, Fn2. So in our system, we have downward forces m1g and m2g respectively, and the normals are resultant of this in the upward direction, Fn1 and Fn2. Correct? So that is how we'll make free body diagram for the masses m1 and M2. Is that clear to you? So that's how we have done. And as let me repeat, we're neglecting the force of friction also in this particular case. We'll take up the next video where we'll consider force of friction. Okay. And we are also neglecting the mass of the cord since it is a very light cord. So what we have done here is the first one, the force Fp acts on the box 1. Box 1 exerts force Ft on the connecting cord, and the cord exerts an opposite but equal magnitude force Ft back to box 1. Correct? So that's the first case as mentioned here. The second was, since the cord is considered to be massless, the tension at each end is the same. Hence, the cord exerts a force Fp on the second box 2. This force can only pull and not push. So that is very important to understand. Is that clear to you? Perfect. So remember that the force exerted can only pull and not push. So free body diagrams I think are clear. Let's move on and solve making equations with these free body diagrams. So in the very first case, what do we notice? We notice that horizontally and vertically, we have to match up the forces. So we have external force Fp applied, the tension reverse direction. Their difference is always positive since we are pulling and we are trying to move the object. Object is moving at a constant acceleration, and that acceleration is a. So, in the first case, since mass is m1, the two forces difference is equals to m1a, we get our first equation. In the case of second equation, we have only a horizontal force which is due to tension moving it along the right direction, which gives you the acceleration of a, the same acceleration, correct? So in both the cases, we have the same acceleration a, right? So acceleration a is constant, it is same in both, correct? And therefore, from the Newton's second law directly, we get our equations Ft equals to m2a. Now to solve these equations, we are only having two unknowns, the tension and acceleration. So first, let's add them, right? So add these equations. Let's call this equation as equation 1 and let's call this equation as equation 2. So let's add equation 1 and equation 2. So when you add them, what do you get? Fp minus Ft plus Ft on the left hand side, m1a plus m2a on the right hand side. Now Ft cancel, positive, negative, and so we get the value if Fp is A times m1 plus m2, the sum of the masses. Rearrange, acceleration is Fp over m1 plus m2, 40 over 10 plus 22, and we can calculate this answer. 1.82 meters per second square, correct? Now remember one thing, that the units, we have taken 12.0, 10.0, right? All these. So we are actually looking for three significant figures, right? So we have to round them to three significant figures. So that is why I've written the answer as 1.82 meters per second square. So many times it may not be mentioned here, but then when you read the question, it becomes clear that you should be writing your answer to three significant figures, correct? Right. Now you recall in our previous example, we actually, if we treat the system as just one, then we can actually find acceleration directly, 40 divided by 10 plus 12. And that's what we got here, correct? So this is our first formula. Acceleration is the force which with the whole system is being pulled over the mass of the system. You get the idea, right? So actually we can generalize this. There could be many number of masses or boxes connected. In that case, we get a general formula as mentioned here, correct? Okay. Now what is the tension? To find the tension, we look at the last box, right? So to find the tension, we look at the last box. In this case, the last box is box number 2. Multiply that with the acceleration to find the tension, since that is the only force acting on it, right? So that is the tension. Perfect. So once you do that, multiply 12 by 1.82, which we just calculated, you get 21.8 newtons as your answer. So once again, this could be generalized. So the last box will give you the tension and MNA, and that gives you Mn. And if there are n boxes, then the last box is Mn, right? To find calculate tension, look in the last box. So what I'm trying to say here is, here's another example for you, a question for you to practice. So what we've done this time, instead of just having two, we have four boxes with the masses M1, M2, M3, and M4 connected. Here's the question for you. Please read the question and answer. Question is, force Fp is applied to pull four boxes with the masses M1, M2, M3, and M4 with constant acceleration a meters per second square. They are connected by inextensible flexible light cord as shown in the figure, right? That is, and this is the constant acceleration with which the system moves. Find the external force Fp in this case, right? So you can find that Fp is what? Fp is sum of the masses into acceleration, correct? So simple as that. So when you connect all the forces, you could actually treat this as one system. You get the idea. You can treat this as one system. And so we are looking into the sum of the masses as shown here into acceleration, and that is equal to Fp, right? So external force we have found. Find the force exerted by the cord on the third box. So we have to find what is this F3, and then we have to find the tension in the cord between 2 and 3. Well, tension is same, right? So F of T is same all along, correct? Remember that. So even if you want to find between what, second and third, ft, you can find here also, right? Both will be same, correct? So that's the concept. So I hope you understand the concept. Pause the video and answer clearly. For as far as the tension is concerned, you should look at the last box, correct? So look at the last box for F tension. Do you clear, right? So that becomes your answer. So note, particles connected by inextensible string moving in the same direction can be considered a single system, and that is absolutely clear from what we have done, correct? So that is what we're trying to say. I hope it makes sense now. So any question where many masses are connected and they are along the same horizontal plane connected with the cordless string, you could solve the questions very easily as we have done here. Now moving forward, we'll take examples where we'll flip the direction of one of them. So here in example 2, we'll use gravitational force. So those are the second level of questions which we need to understand. So now again, we have the same two masses. However, what has happened now? One of them is hanging with the pulley. So the question is, two boxes with mass M1 and M2 are attached at the end of a light inextensible string. The string passes over a fixed light pulley as shown in the figure. Find general expression for acceleration of each box and the tension in the cord. Okay, so free body diagram we have shown here. So look at this box, for example, M1. It is being pulled by the force of gravity. M1G is the external force which is being applied here, right? So this becomes the external force, right? It is due to gravity, correct? Now, this is trying to pull, and then we have acceleration A, with which the object is moving downwards because of this gravitational force. When it pulls, there will be a tension in the string which acts in the opposite direction at the point of the pulley. This tension is transferred with unchanged, same at both the ends as shown here. And finally, this tension comes to the second object, box 2, with mass m2, and here it exerts a force of pull, and so it is going to pull it in the right direction. But the acceleration of the system will remain same as given in the question, right? So that is it. That's given in the question. Now from here we can actually write down our equations. So the first equation comes from this particular portion where we can clearly see that the difference between the two forces. So what is the net force? The net force which we're talking about is basically is m1g minus the tension, right? So that is the net force, and this net force is equal to the acceleration right there, correct? So we get one particular equation writing the net force and relating it with mass and acceleration. That is Newton's second law, correct? So we're talking about Newton's second law. Now at the other object which is right here, if we look at this object, in that case we see what is the result? Well, there is only net force Ft acting, the mass is m2, and the acceleration is a. So Ft is m2a. So we get two equations here to work with. Perfect, just as we got it in the last example. Now with these two, we can always eliminate Ft by adding them up, finding acceleration, simple as that, and then rearranging and finding Ft, multiplying acceleration with m2, right? So here is the solution. So we have these two equations which we are calling as our equation number 1 and equation number 2. Equation number 1 is based on this, right? So that is our equation number 1, and this gives you the equation number 2. Correct. So these are the two equations. We just add them up. When you add them up, Ft and Ft cancel, and therefore what do we get? We get m1a and m2 be on this side, and we have m1g on the left side, correct? So m1g is equals to m1a plus m2a, taking a common, m1 plus m2 isolate, right? So m1 divided by the sum of the masses into gravity gives us the formula for acceleration, correct? In this particular situation. Now Ft, the tension, is mass, second mass. We are calculating from the last mass which is there, multiplied with the mass m2, and acceleration. Acceleration we already know is the ratio of m1 over the sum of the masses into gravity. And so we get the formula for Ft. So that becomes a general formula. So if you're given some values, you can always substitute these values and calculate your answer. I hope the concept is absolutely clear, right? So let's move forward. And then now what we have done here is we have the same question, but we are trying to do calculations. The idea is that ultimately deriving a formula and then finding the values, using some values, is the thing required in the test, right? So the question now here is, two boxes with the mass m1 and m2 are attached at the end of light inextensible string. The string passes over a fixed length pulley as shown in the figure. Find acceleration and tension accurate to one decimal place if m1 is 6.0 kg, m2 is 4.0 kg, right? So we are saying accurate to one decimal place, right? We have specified. So to one decimal place, we'll find the answer, correct? Okay, we are given the mass of both the objects in this case, right? So let's find the acceleration. Well, we'll use the formula directly. Acceleration is the ratio of these masses. Substitute the values, multiply by g, which is 9.81. So what you get is 5.886, one decimal place it is being rounded, and therefore we get our answer as 5.9 meters per second square, correct? The tension, we just calculated that the formula is m1 m2 over m1 m2 times g. We substitute the values and calculate, round it to one decimal place, and so our answer for the tension is 23.5 newtons. So read the question carefully and then write the exact answer as required by the question. And here we are rounding to one decimal place, correct? Now let's take up the third type of example. Now in this particular case, we are hanging the two objects with a pulley. So here we have a pulley. Now see, this pulley right at the center is pinned and it's very free to move. Mass of the pulley is neglected, rotational friction is not there, rotational inertia is not there, and therefore the tension in both the strings is exactly the same, right? So this tension here, both the same, right? So F of T is equal. Do you understand? In both the sides. So that is what pulley assumptions are, which we took in the very beginning. Let's look into the question now. Two boxes with mass of m1 and m2 are attached at the end of a light inextensible string. The string passes over a fixed light pulley as shown in the figure. Find general expression for acceleration of each box and tension in the cord. Is that clear? So cord and string is one and the same thing. Let's have a free body diagram now. So what we are doing here is look at each mass. M1 is exerting a force m1g downwards due to gravity. That causes tension in the string Ft. So that is one part of it. And the whole system is moving with acceleration of a. So it is non-equilibrium, correct? So let's summarize our learnings. Non-equilibrium since we have an acceleration a, right? And therefore, so we know that the net force is equal to mass into acceleration. So that gives you the first equation right there, right? So this is our first equation, and that is what the net force is, right? So this is your net force F, which is at 1. Is that clear to you? Now, let's look into the second one, and the net force F2 is what? So, in the second case, the mass is m2, and therefore it should be pulled down by m2g. However, the system moves upwards. That means Ft was greater. It's better to write Ft minus m2g equals to m2a, right? So, you could write this, and we get our second equation. Do you see that? Simple as that. These equations are very similar as you can see in the three examples, right? So let's look into how do we solve them. Well, these are the two equations which we are talking about, equation 1 and equation 2. Let's look into the system of the equation also once again. Boxes are moving in different direction, and so we will consider the two systems, right? Not single system as in the first case we could. You cannot now combine m1 plus m2. They will have the same acceleration and the tension because of the flexible, inextensible string and the light pulley. Now, these are the explanations which help you to communicate better when you solve the questions. Perfect, important things, and that's why I mentioned them separately. Okay, how do we solve these two equations? Just add the above equations. Once you do that, as we did earlier, you have the expression for acceleration, which is now. You can see the numerator is difference of the two masses. Denominator is same, the sum of the two masses into acceleration. So that helps you to correlate all the examples which you have done so far. Does make sense to you? Right? Now, let's go to the next part and calculate the tension. We already know now the acceleration is m1 minus m2 over m1 plus m2 into g. We have this formulas with us. This was our equation 1, this was our equation 2. Correct. Now, with these equations, what we do? We need to now just solve for ft, right? So what could you do? Well, simplify. Let's go here. Okay. So we know Ft is m2a plus m2g, right? So look at this, please. Ft is m2a plus m2g. So m2g is here, m2a, m2, and for a, I have written down this value. So a is this. So substitute the value of a in the second equation, correct? After adding, correct? Do you see that part? So Ft is rearrange. Ft is take M2G to the other side and M2A, right? So from here we are going this place. Let me highlight, not this. So yeah, basically the same thing, correct? Same things. So take it to the right side, yes. So take M2G to the right side and then from here you go there, correct? So substitute the value of A. Now we know, simplify this. M2 into M1 minus M2, do your math. M1, M2G is common, correct? So take M2G common. We have got this fraction here plus 1, simplify, and you get your formula. So the formula here is 2 times M1 M2 over M1 plus M2 into G is the tension, right? So remember, it is 2 times, and the reason being that these are the two tensions which are acting upwards, correct? So tension is twice in this particular system. So in the pulley, it is easier since upward force is multiplied by 2. Do you see that? When you're just pulling it horizontally, it is Ft. Now when you're doing it with a pulley, with two strings, there are two forces which are acting on it. Do you see that part? So basically you can say a system, but on this system, we are acting Ft. This is Ft, another Ft, and that results in 2 times M1 M2 over M1 plus M2. Do you see that? So twice. So that is the thing, right? So you have twice the force acting upwards. Now that brings us to the end, and we'll now calculate the values. We're taking an example. So here is an example with you. So what I have done here is given the values to the two masses. Two boxes with mass M1 and M2 are attached at the end of this light inextensible string. The string passes over a light pulley as shown in the figure. Find the acceleration and the tension. Mass M1 is 6 kg, M2 is 4 kg, right? So we have given values to these masses. Acceleration is difference of these masses divided by the sum times g, and you get a value. Now, in this particular case, you should write your answer to one significant figure, correct? So we rounded this to one significant figure. Acceleration should be 2 meters per second square. Ft is twice m1 m2, so twice 6 times 4, divided by is the sum 6 plus 4 times the gravity 9.81. We get a value which should be rounded to one significant figure. So we wrote this as 50 newtons, correct? That is very important. Okay, so let's look at the beautiful summary now. So the summary here is we took these three examples, right? So in these three examples, what did we learn? In the very first case, the acceleration is always, because we're talking about the Newton's second law, right? So basically, in Newton's second law, acceleration is equal to net force over total mass. Is that clear to you? Now, in this particular case, see, use net force is Fp, which is acting on it. Total mass is m1 plus m2. We get our formula for acceleration. Perfect. In the second case, you look into the acceleration. It is due to the mass m1. Do you see that? Not due to m2, because this is hanging. The force is actually being applied only to m1. And therefore, the net force which goes into is m1g, right? So this net force is due to Fp is because of m1g, right? Do you see that? And therefore, we have m1g in the numerator. So that's what I'm trying to say. Fp is m1g. If you substitute that here, you get the same formula. Now in this particular case, because one is acting downwards, the other one moves up, we are looking at difference of forces, right? So in this case, Fp is basically the difference of the two, right? m1 minus m2 times g. And that is why the formula has in the numerator m1 minus m2 times g. So that is how the acceleration is. Now, once you relate all of them, it is so easy to solve. You don't have to derive or remember them, right? It is obvious. So we are looking into the net force and dividing by the total mass, correct? And we get our acceleration. Perfect. Now, let's talk about the tension. As far as the tension is concerned, tension in string, right? It is what? It is the last object. For the tension, we have to look into last object. So, which is this in this case, and we know m2a. Acceleration is constant, right? A is constant. So just multiply the two to get the tension m2a, and we know a is from here, right? So use a, which we have already figured out is this. And you have your formula. Do you get the idea, right? So that is how you get your formula for tension in all the three cases. Here the last mass is m2, and so it is m2a. Just substitute the value and get your answer, right? F, and it comes down to the product of the masses divided by the sum when you simplify into gravity. Clear, right? Now, for F2, in this particular case, since there are two masses here, it becomes two times the previous. Do you see how they are related? Now, because there are two tensions, correct? Ft, right? If there were n, then this will be n. You get the idea. Perfect. If we have a system pulleys with n number of strings, this will number will be n, right? So n strings, ft will be what? N times m1 m2 over. So if we add the number of strings with the help of some pulleys, in that case gets multiplied by n. And so there we have a mechanical advantage. Do you see that? Mechanical advantage. It's much easier to use pulleys with number of strings. And that really summarizes what we have learned. So from here, you can also solve examples with n boxes and with n strings. Do you see how we have learned? And that is how we should be working on. So the whole system can be escalated to n number of boxes and n number of strings. With that, we come to an end of this lesson. I hope it really helps. In case you want any clarifications, you can always write to me on the email and check our website for the latest videos. I hope that helps. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.